Hello, in this video we're going to solve problem 10 from chapter 11 from this book, An Introduction to Statistical Learning with Applications. It's a free book to download. It's absolutely amazing, and I would recommend that you all do that. For the problem 10, it says plot the Kaplan-Meier curve with one standard error bands using the SURFIT function. Now this is taken straight from the book, and then the solutions are mine. So we need the package for the data set, brain cancer. We need the survival package. We fit a survival curve to this, so this sets it up, the capital SURV, and then we plot it and we get this curve here. Now I'd like to point out the default for the confidence intervals is 95%, and if you think about the standard normal curve, 95% corresponds to 2 standard errors, and we wanted 1 standard errors. And so under the standard normal curve, that's about 68% of the data, or the area under the curve. So we put 68%, and this is essentially a 1 standard deviation curve. Now we're also going to bootstrap these estimates, these standard errors, and I need to point out a few things that to consider as we move along. So I rug the times, and that just means it puts a slash at those specific time points. So these are the time points that we want to estimate. So we'll take a bootstrap sample, and then we'll use these specific times to estimate survival using the model that was generated from the bootstrap sample. Now here's the caveat. In this, for example, in this model, if we estimate the survival time at, say, 90, which is outside the scope of the model, R, doesn't do it. It's like, nope, I'm not trying. So it creates an error or a missing value. So there might be, should we just carry this forward, or should we half it, or zero? So it's not obvious the best thing to do. The reason I'm pointing this out, when we bootstrap sample, some of these larger values, this largest value may not make it into that bootstrap sample. So when we use this time to estimate the survival, but the model scope doesn't include that, so we get an error when we use this. So do we leave it missing, or do we carry forward this last observation? So those are the things to think about. So in part B, it says draw a bootstrap sample size 88 on the pairs of data. Let's repeat it 200 times, and then obtain a standard error of the survival curve, and then of course compare it to part A. So here I use this is a function that is a last observation carried forward function. So if you have missing data sets at the end, whatever the last one is, it'll carry it forward. Actually, it works for the interior too, but in this bootstrap program, it only missing is at the end. We'll highlight that more as we go. We want 200 bootstrap samples. Here are the unique times that I want to estimate, and I notice that I add 0 because I want it to start at 1. If you leave off 0, then it starts at the first time, and I want the curve to include 0. I want the unique values of time. I sort them, and so they're all in the same area. This is the matrix that I'm going to store these results. The rows, the number of rows corresponds to each unique time, and then the columns is bootstrap. So each column represents a bootstrap sample and the estimates involved in that. We create a for loop from 1 to however many bootstrap samples. We sample from our brain cancer. This actually creates the observations that we're using in our bootstrap sample. We fit the survival curve with that bootstrap sample. We store it in here. Now we use this curve, but we want to estimate the survival at these specific times with this function that we just created, and then we summarize it, and that creates a whole array of different values. But we only want the survival fit of that. and we store it in here. So it's a vector corresponding to these times. Now the downside is if in our Bootstrap sample we don't grab that last value, but then we use that value to estimate survival using this function that we created, it's missing. It's actually more than missing. It's just not there. And so I checked the length of our estimates to see how many were not included, and then we store the results in the ith column from 1 to however many there are. Now, if we just take these estimates and store it in the ith column, if we grabbed that last observation, then there's no error. It just stores it in the columns. But when the vector is shorter than the length of the number of rows, we get an error. So I have to tell it to store it in there. Now, the last few observations we could leave missing and then create standard deviations, just remove those and create standard deviations. But here I'm showing you the last observation carried forward technique, so every row and will have a value in every column. We create the standard deviations of these estimates that we created. I calculate a mean, which we don't need to do. I just think it's kind of cool to look at the plot. This is the original function, the estimate Kaplan-Meier curve from the brain cancer with one standard error, and then we create lines according to the fit, and then the standard one standard deviation errors. We legend, and this is it. And this is so cool that you can see the black and the red are essentially right on top of each other, and especially the Kaplan-Meier estimate of survival. Now, if you were to leave the last few rows of each column blank when that Bootstrap sample didn't include the largest or largest two, it affects these standard errors at the end, and you can see a slight bump right here at the end if you were to do that on your own. So now part C, it says fit a Cox model. We're using all the predictors, and so it's just the standard Cox pH function and the dot says include them all. And this is the printout here. P-value for the model is highly significant. Gender or sex is not significant. It looks like that diagnosis is significant in the model. Ki is significant. GTV is marginally significant. And that's how I'd interpret that. Part D, stratify the data by Ki values. So what we want to do is the Cox model creates a summary of the parameters or variables that we're using to help us predict survival. Well, what if we want to generate survival curves for the different levels or values of Ki? Well, that's what this next problem is dealing with. We want to create survival curves for specific linear combinations of our variables, and so but it notices that there's only one Ki value of 40, and you can get wonky estimates with only one unique value. So they suggest just recoding it to 60 and then plotting the rest of the Ki values. So here is how I would recode 40 as a 60, so within brain cancer, so I stay within that data frame. I create a new column, Ki2. I find where the Ki values equal 40, so this is going to be a vector of trues and falses, and wherever it's 40 I shove in 60, and I store that back into the data frame. Now it's always good to check to see if your values did get coded as you think, and notice that the 70s are the same, the 80s, the 90s, the 100s, and the Ki 40 was coded to 60. The 60s of course stayed 60. So we fit a new model with using Ki2, and now we have to print or create survival curves. We have to create a new data set, and we have to pick values for each of the variables in our model. And we want the different values for Ki2. And these are the values that Ki2 takes on, and these are the different survival curves. So now we want to hold the other variables constant. And so we pick a level for sex and just female. We pick a level for diagnosis. We pick a level for location and we rep it 5 times. Stereo, we pick a value. Oop, I don't know what happened there. And then since GTV is continuous, let's just pick the mean value and rep it 5 times. One might argue that when you create a histogram of GTV, it's pretty highly skewed to the right. So maybe the median is a better representative value for GTV, and so you could put the median here and then rep it 5 times. Regardless, you get similar plots, and so I just use the mean. We want to take our Cox model, use new data that we created up here, create survival fits for these different combinations, and there's only 5 because store it here. We plot it. We plot the new estimates, and this is it. And so these are the different values for the KI. And you can see that as KI increases, the hazard decreases, or you could think of it as the survival increases as these estimates. And this is a pretty significant difference, and that's why it was significant in the model. Okay, well, that's all I have for this video. Stay tuned.